In today's lesson, we are going to continue to look at trig identities. So we're just going to jump right in. We're going to use the same kind of rules that we looked at before. Some of those, the quotient identities, the reciprocal identities, the different, and the Pythagorean identities. So we're going to be using those to help kind of prove these statements. So to start with the first one, we want to prove that sine theta equals secant theta, or sorry, sine theta times secant theta times cotangent theta equals 1. Right, so again, kind of looking at this, think back to some of the rules, right? We want to split it up into left side and right side first. So right side equals 1, can't do anything further with that. On the left side, we have sine theta times secant theta times cotangent theta. I don't want secant or cotangent. I want to remove those. I want mostly sine and cosine. So I'm going to use my reciprocal identities to replace secant and cotangent. So I'm going to have sine theta is equal to, or times 1 over cos theta times 1 over tan theta. So again, just using those reciprocal identities, we can kind of see here, these reciprocal identities over here. I can now multiply all of this through. I have sine theta times, would be sine theta over cos theta. That's going to multiply 1 over tan theta. But before I go and multiply these two together, right, if I bring up those reciprocal or those different identities, I do see that sine over cos is equal to tan. Right, so what I'm going to do here, I'm going to use actually my quotient identity, replace the sine theta over cos theta with tan theta. Tan theta times 1 over tan theta just becomes tan theta over tan, which is 1. So therefore, looking back, I now have left side equals right side. I have 1 on both sides. And so that is proven. Next, we're just going to go through a couple examples, look at a couple of different ways that you could solve, or a couple of different things that you might have to do when you're solving these trig identities. So we want to prove that cos x equals 1 over cos x minus sine x times tan x. Left side's pretty straightforward. Cosine x, I'm just going to leave it there. On the right side, a little bit more complicated. 1 over cos x minus sine x times tan x. I'm going to replace the tan x. Right? I'm going to replace that with our quotient identities. So I'm going to have 1 over cos x minus sine x times sine x over cos x. I'm going to multiply those two together, try to simplify things a bit. I get sine squared x over cos x. I can actually subtract these. I can combine these fractions. 1 minus sine squared x over cos x. And then I need to somehow get this right side to equal cosine x. But we should recognize, or maybe we recognize, that 1 minus sine squared x is one of those identities that when we squared the Pythagorean identity, over here we can see that cos squared theta minus or equals 1 minus sine squared theta. So I can use a Pythagorean identity and rewrite this as cos squared x over cos x. Using our power rules, right, or canceling out, because if this could be rewritten as cos x times cos x all divided by cos x. So one of those cancels each other out. We're left with cos x which is what we have on the left side as well. Oops, can't see some of that. So cos squared x could be written as cos x times cos x over cos x. Cancels out. We now have left side equals right side. So again, we've proven this statement. Next one, 1 over 1 minus sine x minus 1 over 1 plus sine x equals 2 tan x divided by cos x. So a lot of stuff going on here. I'm going to split the two sides up. So 1 over 1 minus sine x minus 1 over 1 plus sine x. And then we have 2 times tan x over cos x. It doesn't really matter which side you start on. You might have to kind of jump back and forth depending on what you're comfortable with, or how far we get. Right? I'm going to start with the right side because I know I want to get rid of the tan x. So I'm going to use my quotient identity to get rid of the tan x. So it's going to be 2 times sine x over cos x all over cos x. I can simplify, or I can divide this, right? Because if I'm dividing this, it's the same thing as saying 2 times sine x over cos x. Instead of dividing by cos x, I'm going to now multiply by 1 over cos x. And I get 2 sine x over cos squared x. So I've simplified everything there as much as I can without kind of going back and converting things. So let's move to the other side. Let's see if there's anything I can do. Well, I do want to add these two fractions or subtract these two fractions. I'm just going to rewrite them to make them a little bit bigger. So 1 over 1 minus sine x minus 1 over 1 plus sine x. So in order to add them or subtract them, I need a common denominator. So I need to multiply both sides by the other denominator. So 1 minus sine x and then 1 plus sine x. I'm just getting a common denominator. On the top, 1 plus sine x over, on the bottom becomes a difference of squares. Right? So it becomes 1 minus sine squared x and 1 minus sine x. So I haven't combined them yet. I just multiplied multiplied each fraction so they now have a common denominator. Now I'm going to combine them. So I have 1 plus sine x minus 1 minus sine x all over 1 minus sine 2x. The top, if I'm subtracting everything from the second term, that becomes addition. So it should be minus 1 plus sine x. So if I have 1 minus 1, that's 0. Sine x plus sine x is plus 2 sine x over 1 minus sine squared x. I get 2 sine x. And on the bottom, right, if I look on the right side, I do want that cos squared. So I am going to use my Pythagorean identity to change the bottom, because 1 minus sine squared x is cos squared x. And now I have a left side that equals a right side. Moving on to the next example, again, getting a little bit more complicated. So we have sine theta plus cos theta squared plus sine theta minus cos theta squared equals 2. I'm going to start with the right side. That's easy. It's 2. I don't have to do anything further to it. The left side is going to get a little bit complicated. So sine theta plus cos theta squared plus sine theta minus cos theta squared. Now we want to expand these, right? We want to expand them to kind of get a better idea of what we're dealing with. You can use them with sine and cosine, but because we're going to be simplifying, I'm just going to let x equals sine theta, and I'm going to let y equal cosine theta. All this is just to basically rewrite this so it's a little bit simpler as we go through and expand. So I'm going to rewrite this as x plus y squared plus x minus y squared. Right? I'm going to expand these now. Right? So x plus y squared becomes x squared plus 2xy plus y squared. And the second one is going to be the exact same, except x squared minus 2xy plus y squared. I'm going to collect my like terms. So I have 2x squared. The 2xy cancels out with the other 2xy. So I have 2x squared plus 2y squared. These two cancel out. I can then common factor, take a 2 out. 2 times x squared plus y squared. I'm now going to resubstitute or substitute back in. I've kind of simplified as much as possible. So I'm going to substitute back in the x squared plus the y squared to become sine and cosine. So it would be 2 times sine squared theta plus cos squared theta. And the last step, looking at what's in the brackets. Oh, okay, that I should recognize that that is a Pythagorean identity. Sine squared plus cos squared theta equals 1. So this becomes 2 times 1, or 2. And again, that equals now my right side. So left side equals right side. So again, in some cases, if we have to expand, it might be easier to replace the sine and the cosine or whatever the ratios happen to be with a variable, just as a placeholder to make it a little bit easier as we kind of cancel things or expand things. Last example, we want to prove that tan x plus cos x divided by 1 plus sine x equals secant x. So left side and right side, let's write those out. Tan x plus cos x over 1 plus sine x. On the other side, we have secant x. I'm going to deal with secant x first because, again, it's just one thing. I'm going to use my reciprocal identities to change this to 1 over cosine x. I'm going to go back to the left side now. I want to rewrite some of these. So I'm going to use my quotient identity to get rid of tan x. So I have sine x over cos x plus cos x over 1 plus sine x. Now I do have fractions and I need to get a common denominator to add them. So I'm going to multiply the right fraction by cos x, both parts, keep it equivalent, and 1 plus sine x on the other side. This becomes sine x times 1 plus sine x over cos x times 1 plus sine x plus cos x times cos x all over, again, cosine x times 1 plus sine x. You probably could simplify this a little bit sooner if you're more comfortable with this. I'm just kind of trying to show all the steps just so you don't get kind of confused on how we kind of skip from one to the next. So I'm going to expand all of this. So I'm going to have sine x plus sine squared x, so distributing this. The other one is going to be plus cosine x squared. All divided by cos x plus cos x sine x. On the top, I could look at this as, if I look at just the two brackets here, right, oops, wrote backwards, cos squared x, right, up there, that is a Pythagorean identity, right, seeing the sine squared x plus cos squared x. So this would be the same as saying sine x plus 1 over, and I kind of went a bit too far, because if I wanted to keep things kind of separated into factors, right, I might want to change the bottom back, because if I change that back to 1 plus sine x, right, retake that factor out, or undo the factor, or common factoring, or the expanding that I did, right, I should see that sine x plus 1 over 1 plus sine x, those will cancel each other out, the entire thing, and I'm left with 1 over cos x, which is the exact same thing I had on the right side. Right, and now I have left side equals right side. So again, that's kind of an example of why when we looked at the rational expressions, we said to kind of leave things in their factored form, because it does help to cancel out. So I kind of jumped the gun a bit and went too far and expanded again, when I probably would have been better off to leave things unfactored. So again, this is just more practice looking at the different trig identities, looking at how we can use them, some different examples of things we might have to do, such as in example 2, where we had to simplify, or we had to substitute our ratios for variables just to make it a little bit easier. Not that you couldn't do this with the sine theta and cos theta in there, it would just probably get very long and a little bit more confusing. A lot more parts that you have to kind of be aware of. But again, the main thing is just, again, using the trig identities to prove these statements.